Alright. I'm going to be honest, we're going to cheat the system a little here and I'm going to jump ahead. So really, if you think back to the first test when we did derivatives for the first time, I made you do the limit definition where we had to cancel out the delta x's, we had to do all sorts of fraction math in order to get down to an answer, and then when we came back the next class after that test, I started showing you the easy way with the power rule and other ways to get to the same idea. Here, we're doing distance learning. I am going to skip the hard way. So instead of showing you this way of doing things, which is how they do it in the book, I'm going to jump right to the real way of doing things, which is using the integration formulas we used in 4.1. I will say that that might lose a little bit of the general idea of why we're able to do area. Essentially, if we use the limit definition, you'd see that instead of our rectangles being length 0.5, we start shortening that length until they're infinitely small. If they're infinitely small, we're really adding together so many rectangles that we're getting a perfect approximation of the curve because the distance between any one rectangle is effectively 0. So it is an interesting transition to get from this limit definition to what we're going to do, which is using the fundamental theorem of calculus. But I just feel like it's not worth you guys trying to figure out all the summation formulas and the conversions of the hard way instead of just showing you the easy way out. So basically, what we're going to be doing is the same way that we did indefinite integrals, we're going to be using the reverse power rule. So here, when I have a 3, I'm going to call it 3x when I integrate. Normally, you would call this 3x plus c if it were an indefinite integral, but because there's numbers on the integral, I don't have to worry about that plus c. What I'm really going to do is put a line after the 3x with 0 and 10. What that tells me is I'm going to plug in 10 everywhere where I see an x first. Then I'm going to subtract from that, plugging in 0 wherever I see an x second. 3 times 10 gives me 30. 3 times 0 gives me 0. So my final answer here would be 30. You may be asking, how come we don't need a plus c here? The general idea is I could have put a plus c here, but then I'd put a minus that same exact constant here. So since the constant minus the constant is always going to cancel each other out, I don't need to worry about that constant when I'm doing a definite integral. Moving on to part B. This asks me to integrate x dx. I add 1 to the power that used to be 1. It becomes x to the second. I divide by the new power, 2. This would have been the answer if it was an indefinite integral, really plus c. Because there's numbers on the integral, I need to evaluate at those two numbers. So I write my evaluation line from 3 to 7. I start by plugging in 7. 7 squared over 2. Then I subtract when I plug in 3. 3 squared over 2. 7 squared gives me 49. 3 squared gives me 9. So it becomes 49 over 2 minus 9 over 2. That gives me 40 over 2, which is really 20. If I now go to the final problem on this video, where I'm going from 1 to 17 of 5x squared dx, I can consider that the same thing as 5 times the integral from 1 to 17 of x squared dx. When I integrate x squared, I add 1 to the power, so that gets me to x to the third. I divide by the new power, divided by 3, and I want to go from 1 to 17. I definitely don't know what 17 cubed is, let alone 17 cubed divided by 3. So let me put that in my calculator. 17 to the third power gives me 49/13 divided by 3. From that, I'm going to subtract 1 cubed, which is 1, divided by 3. So this is going to become 5 times 49/12 divided by 3. When I put that in my calculator, 5 times 49/12 divided by 3. It gives me 8186.67.